Welcome to another deep dive. And today we're going to be looking at the fine structure constant,
Okay.
which is something that I know you know a lot about.
Yeah.
This number 1 over 137.
Right.
It's just kind of been hanging out there.
Yeah.
And it seems like every few years or so, there's some new idea about what this number actually means.
Right.
So I guess the big question that we're tackling today is it just random chance that it's this number, or is it a clue
Yeah.
to something much, much, much deeper
Exactly.
about the universe?
Right.
And we have, sources that are suggesting some pretty wild things, like it could be a geometric property of space-time itself.
Yeah.
Um,
It's intriguing, right? This constant that appears to be dimensionless, but it somehow governs the strength of electromagnetic interactions
Right.
at the quantum level.
Yeah.
And if we can connect it to geometry, it could really revolutionize our understanding of how forces work.
Okay, so let's break it down. We're talking about this number about 1 over 137.
Right.
That basically dictates how strongly particles like electrons and photons interact with each other.
Exactly.
But I guess the big leap here that our sources are suggesting
Right.
is how do we get from this number to
Yeah.
the vastness of space-time?
Yeah. So the sources, they're suggesting that the fine structure constant, which we often represent as alpha,
Okay.
could be a result of how waves
Okay.
interfere with each other
Yeah.
at the quantum level.
Okay.
So you can imagine like waves in the ocean colliding.
Okay.
They can amplify or cancel each other out.
Got it.
Our sources suggest something similar might be happening with the fundamental waves that make up space-time,
Okay.
and alpha could represent a kind of limit on these interactions.
So we're not just thinking of alpha as a number.
Exactly.
We're thinking about it as like a consequence
Right.
of how the very fabric of reality
Yeah.
vibrates
Yes.
and interacts.
That's a pretty wild idea.
Yeah, that's crazy.
Mm-hmm.
And I noticed that several of our sources mention the golden ratio.
Right.
Is that
Yes.
playing a role in this?
Absolutely.
Tell me more about that.
So the golden ratio, represented by the Greek letter phi,
Yeah, I know about phi.
Yeah.
Yeah.
It's found everywhere in nature,
Yeah.
from the spirals of galaxies to the arrangement of petals in a sunflower.
Right. So are you saying that the same thing that's telling a sunflower
Yeah.
how to arrange its seeds
Yeah.
is also determined?
It's a mind-boggling question
How strong?
that these sources are
To
exploring.
electromagnetic forces.
Yeah.
Like, how could those two things be connected?
So they suggest that this ratio,
Okay.
combined with the principles of wave mechanics, could actually explain why alpha has the value it does.
Okay.
One of the sources even mention how
Right.
223 divided by 360
Mm-hmm.
is incredibly close to the inverse of the golden ratio,
Okay.
hinting at this deeper connection.
So the golden ratio, which we usually think about as like
Yeah.
aesthetic beauty and natural
Yeah.
patterns,
Exactly.
could be a key
It could be.
to unlocking
Yeah.
one of the most fundamental constants
Yeah.
in physics.
That's what some physicists propose.
Wow.
They're suggesting that the golden ratio, inherent to the structure of space-time,
Okay.
influences how energy is distributed at the quantum level.
Right.
And that ultimately affects the value of alpha.
This is blowing my mind.
Yeah.
I mean, it's like we're finding like a
Yeah.
hidden code
It is.
that connects
Yeah.
this, like the universe's grand design
Right.
with the tiniest particles.
Exactly.
Okay, so our outline also mentions black holes
Yes.
and quantum singularities.
Right.
How do those fit into all of this?
Well, remember, we're kind of exploring this idea of alpha being this emergent
Right.
geometric property of space-time.
Right.
Black holes are regions where space-time is warped to its extreme.
Yeah.
And some sources propose that alpha might actually define a limit on how energy behaves
Okay.
near a black hole's event horizon,
Yeah.
that boundary beyond which nothing, not even light, can escape.
So you're saying this seemingly simple number
Yeah.
could be dictating how energy interacts
In the most extreme,
in the craziest parts of the universe.
gravitational environments in the universe.
Yeah.
Precisely.
Wow.
And it gets even more intriguing.
Okay.
Our sources delve into the concept of quantum singularities,
Yeah.
points in space-time where our current understanding of physics breaks down.
Right.
These are thought to exist at the center of black holes and possibly even at the very beginning of the universe.
All right. So now we're talking about like
Now we're getting into
some mind-bending territory.
crazy stuff.
Yeah.
So quantum singularities, how do they relate to the fine structure constant?
Well, some sources suggest that the fine structure constant might be a direct manifestation
of the geometry and behavior of these quantum singularities if they possess fractal properties.
Okay.
A kind of self-similarity across different scales.
Got it.
They could be the source of patterns that permeate all of reality, influencing the value of alpha.
So we're suggesting that the structure of space-time at its most fundamental level,
Right.
these quantum singularities, could be reflected in this tiny constant
Yeah.
that governs the strength of electromagnetism.
It's a profound idea.
That's a pretty profound idea.
Yeah.
Wow.
And if true, it implies that the laws of physics as we know them
Yeah.
might not be as fixed as we once thought.
Oh, wow.
Okay.
Yeah, we've gone from waves in the ocean to the edges of black hole.
We've gone.
And it seems like we're just getting started.
Just getting started.
So I'm really curious to hear more about the mathematical frameworks.
Yeah.
And how scientists are actually trying to test these ideas.
Right.
So I think that's a good place to maybe take a break.
Right.
And we'll come back
That sounds good.
and delve into that a little bit more.
All right. Yeah, so before we dive into the math,
Okay.
it's important to understand why this geometric interpretation of alpha is so compelling.
Right.
You know, for decades, physicists have been trying to derive alpha from first principles.
Right. So, like, find
Sort
some
of stuff.
deeper,
Explain why it has the value it does.
reason for this number.
Yeah,
Rather than just accepting
but with little success.
that it is what it is.
Right.
Yeah.
And that's where these new approaches come in.
Okay.
Instead of looking for a purely numerical explanation,
Yeah.
they're starting to think about alpha as an emergent property
Right.
of the structure of space-time itself.
Okay.
It's a radical shift in perspective.
I see that.
Right. Yeah.
So, but how does that actually, like, how does the math support that?
Right.
Like, our outline mentioned an equation
Yeah.
that connects alpha to pi and the golden ratio.
Absolutely.
You unpack that for us a little bit.
So one of the sources proposes this remarkably simple equation that directly connects these fundamental constants.
Okay.
It suggests that alpha is approximately equal to 1 divided by
Okay.
the product of pi and 4 times the golden ratio squared.
Hold on, I got to visualize this.
Yeah.
So alpha is approximately equal to 1 over
1 over pi times 4
times 4 times
times phi squared.
phi squared.
You got it.
Wow.
And what's really remarkable is that when you plug in the numbers,
Yeah.
this equation yields a value incredibly close to the actual measured value of alpha,
Okay.
like within 1%.
Wow. That is pretty convincing.
It is.
So, like, a number
Yeah.
that's governing the strength of electromagnetism
Right.
at the quantum level can be so closely approximated
Right.
using just like pi and the golden ratio,
Exactly.
which are just like
Which are purely geometric concepts.
shapes.
Right.
That's mind-boggling.
It is mind-boggling, but
So-
some sources actually go even further, suggesting that our understanding of pi itself
Okay.
might need a slight adjustment.
Okay.
You see, in traditional geometry, pi is a constant.
Yeah. 3.14159.
3.14159.
Whatever.
Yeah, we've all learned that in school.
Yeah.
But some alternative models suggest that under certain geometric frameworks,
Got it.
pi might have a slightly different value,
Hold on, wait.
closer to 3.2.
Are you saying that pi
It's a bold claim.
might not be pi?
What?
Like one of the most fundamental
Yeah.
constants in math.
It stems from the idea that our conventional understanding of geometry
Yeah.
might be an oversimplification.
Okay.
Some physicists are suggesting that in the realm of quantum mechanics and space-time curvature,
Okay.
a slightly different value for pi might be needed to account for the complexities we're dealing with.
So like a pi correction.
Exactly.
And fine-tuning to reflect
The weirdness of space-time.
the intricacies of space-time at the quantum level.
Right.
Exactly.
Okay. And what's fascinating is that these alternative values of pi
Yeah.
could lead to an even more precise calculation of alpha, bringing
Right.
us even closer to that 1 over 137 value.
All right, so we're messing with some really fundamental stuff here.
We are.
Like things that I thought were just like set in stone.
Right.
And it's really exciting, but
It is exciting.
how do we actually like test this?
Right.
Like what kind of experiments?
So there are a few promising avenues our sources highlight.
Okay.
One involves high-precision spectroscopy
Okay.
by analyzing the wavelengths of light emitted and absorbed by atoms.
Okay.
Scientists can measure alpha with incredible accuracy.
Yeah.
If the value of alpha were to show even the tiniest variations under different gravitational conditions,
Okay.
say near a massive object like a black hole,
Okay.
it would lend strong support to the idea that alpha is tied to space-time geometry.
So we're looking for changes
Minute shifts.
in, like, the light coming from atoms.
Yeah, in the light emitted by atoms.
To see if maybe
To reveal
alpha is changing.
potential variations in alpha
Yeah.
caused by the warping of space-time.
Because of the warping of space-time.
Precisely.
It's like we're using light
Yeah.
to study
It's like using light as a probe to study the very fabric of reality.
the fabric of reality.
Yeah,
Yeah.
crazy.
Another approach mentioned involves particle accelerators.
Okay.
By smashing particles together at incredibly high energies.
Okay.
Scientists can recreate conditions similar to those in the early universe or near black holes.
Right.
These experiments could reveal new particles or forces that interact according to the principles governed by alpha,
Right.
further solidifying its connection to the underlying geometry of space-time.
So we're creating like little baby black holes.
We're essentially recreating those extreme environments here on Earth.
Here in the lab.
Yeah.
Wow. Okay. And there was one more thing that our outline mentioned.
Right.
Black hole charge and mass ratios.
Yes, that's a key point.
How does that tie into all this? So some sources propose that if alpha sets a limit on how strongly charges can interact,
Okay.
it should also influence the maximum amount of charge a black hole can possess.
Okay, I see where this is going.
Relative to its mass.
So we can study black holes and see if they follow the rules.
Align with the predictions made by this geometric interpretation of alpha.
Of alpha.
Exactly.
It's like black holes are like our...
It's like using black holes as cosmic laboratories.
Yeah, cosmic laboratories.
To study these fundamental constants.
Wow.
There's even a specific equation, the Reisner-Nordström metric, which describes charged black holes.
Okay.
And some physicists suggest we could try to redefine the charge-to-mass ratio in this metric using alpha's wave-derived expression.
Yeah.
And then compare it with real astrophysical data from black holes to check for consistency.
That's pretty wild.
It is pretty wild, right?
Yeah, we've gone from like waves in the ocean
We have.
to like the edges of black holes.
To the edges of black hole.
And now we're like writing equations
Yeah.
about like the most extreme objects
It's a pretty amazing journey.
in the universe.
It is.
Yeah.
It is.
All right, well,
Yeah.
that was a lot.
That was a lot.
Maybe we should take a moment,
Yeah.
let it all sink in,
Sounds good.
and we'll come back and wrap things up.
Okay.
All right, so we're back, and I gotta say,
Yeah.
my head is still spinning a little bit
It is a lot to take in.
from all these crazy concepts.
It is.
We're talking about how this fine structure, constant,
Yeah.
might not be a random number,
Yeah.
but a consequence of the geometry of space-time.
Potentially even connected to the golden ratio and pi.
Yeah, and it could be connected to like phi and pi.
Yeah.
But
You're wild.
it is pretty wild.
Yeah.
Let's bring it back down to Earth for a second.
Okay.
Why should we care about this?
Right. That's a great question.
Like, what does this actually mean for us?
So while these concepts might seem esoteric, they could have profound implications.
Okay. For our technological future,
Right.
if we truly understand alpha and its connection to the fabric of reality,
Yeah.
it could revolutionize fields like quantum computing,
Okay.
energy generation,
Right.
and even our understanding of consciousness itself.
Hold on. Did you just say consciousness?
I did.
How could something like
It's a bold proposition.
the fine structure constant?
But some sources suggest that the principles behind alpha,
Yeah.
particularly its connection to wave interactions and geometric patterns,
Right.
might be relevant to understanding the complex dynamics of the brain
Okay.
and how consciousness emerges.
I mean, our brain is
Let's look about it.
just a bunch of electrical signals.
Our brains are essentially networks of interconnected neurons,
Right.
communicating through electrical and chemical signals,
Yeah.
all governed by the laws of physics,
Right.
including electromagnetism, which alpha dictates.
So we're saying that there's a connection
And a potential link between the fundamental laws of the
the
universe,
laws of physics and the very essence of what it means to be aware
one consciousness.
and conscious.
Yeah.
It's pretty mind-blowing.
It's super mind-blowing.
It really highlights how interconnected everything in the universe truly is.
Yeah.
You know, we've journeyed from the realm of subatomic particles to the edges of black holes.
Right.
And now we're touching upon the mysteries of consciousness itself,
Yeah.
all through the lens of this seemingly simple number, alpha.
It's really making me think about like all the different fields that this could impact.
Absolutely.
If this is true.
It reinforces the idea that science is not just about collecting facts,
Right.
but about seeking deeper connections and underlying principles that govern the universe and our place within it.
Absolutely.
Yeah.
So I guess to kind of wrap things up here,
Yeah.
what are some key takeaways you want our listeners to?
I'd say the most important takeaway is to stay curious.
Yeah.
And to question assumptions.
Yeah.
For decades, we've accepted alpha as a given, a fundamental constant without a deeper explanation.
Just a number.
But by challenging that assumption and exploring new perspectives, we're opening up entirely new avenues of inquiry.
It's like science is never really settled.
Exactly.
There's always more to learn.
There's always more to learn.
Yeah.
And perhaps the biggest question of all is this.
Okay.
If alpha truly is an emergent property of spacetime geometry, could there be other fundamental constants that emerge from the same underlying principles?
Like what else is out there?
Could we unlock entirely new realms of physics and cosmology by viewing the universe through a purely geometric lens?
That is a huge question.
It's a fascinating question to ponder.
It really is. And it seems like we've only just begun to like scratch the surface of this.
We've just scratched the surface of understanding the universe's hidden architecture.
Well, folks, that's our deep dive into the fine structure constant.
The enigmatic fine structure constant.
Right. We hope you enjoyed the journey.
I hope so.
And as always, keep questioning.
Keep questioning.
Keep exploring and keep diving deep.
Keep diving deep.